morning students, myself Sushmita, Assistant Professor ECE RCET. So in this video we will be learning about antenna types and the radiation mechanism that is involved in each antennas. So on completing this particular video you will be able to understand what are the different types of antenna that is present, and also about the radiation mechanism of antenna and how power is being radiated in each different type of antenna. So first, starting up with the current distribution for wire antenna, we know that in order to calculate the electromagnetic fields of longer antennas, we have to first initially know how the current is being distributed along the antenna. Suppose in case if there is absence of one current element, then we have to assume that there is some amount of distribution that is being in that particular antenna, and we have to do the approximate calculation of field distribution. So the accuracy of the fields will be calculated depending upon how the assumption is being made for the current distribution along the antenna. So you can see in the diagram that is given in the PPT. Now we are assuming that the current distributed along the infinitesimally thin antenna is being sinusoidal. So we can say that when the antenna is said to be very thin, then there will be no current in the center point, that is the current is said to be 0 at center, which is denoted as Z is equal to 0 in the diagram. Next thing, if the antenna is becoming thicker, that is in the second case when the antenna becomes thick, then the current minimum increases and there will be a time shift that causes along the end of the antenna. So this is how we are going to assume the current distribution along the antenna. So now we can see about the radiation resistance of elementary dipole with line current distribution. So what is short dipole? Short dipole is nothing but which has an uniform current, which can be also called as elemental dipole. Elementary dipole is nothing but we will be feeding the antenna at the center point with a very length, that is the length of the feed antenna will be very short when compared to the wavelength that is being used. So the current amplitude will be continuously uniformly increasing from the end, and it will be reaching the maximum at the center point. Similarly, the current is said to be 0 at the open end, and it will be said to be maximum at the center when the excitation point is being done. Now let's see the sample calculation of far field components as well as the total current power radiator. So the far field components of the elementary dipole with the linear current distribution can be given as E theta is equal to Im ln sin theta j beta e power minus j beta r divided by 4 pi r. Similarly, H is equal to Lm L sin theta j beta e power minus j beta r divided by 4 pi r. This is the case of far field distribution in the elementary dipole with linear current distribution. Similarly, when we calculate the total power that is being radiated along the current element, then we can say that by giving the surface integral by using the Poynting vector theorem. As we have studied the Poynting vector theorem, when we apply in this case, we can see that power radiated average is equal to E theta high phi divided by 2, which is equal to eta of Lm sin theta square divided by 8 r square lambda square. So this is how the total power is calculated. You can see in the slide the average is calculated as well as the radiation resistance is being calculated. Particular half wave dipole antenna. The half wave dipole antenna is fed at the center by having the maximum current will be placed at the center. So we can say that by specifying the length of that particular antenna, L is equal to 2h and the vertical height of the antenna is equal to L by 2. So when the fields originate due to the current element, we can give it as I dz. So since we are assuming the current flowing in that particular thing is sinusoidal, we can give the equation as I is equal to Im sin beta h minus z for z is greater than 0. Similarly, the vector potential of that particular current element I dz can be given as dAz, which is equal to mu I dz e power minus j beta r divided by 4 pi r. So we can calculate the total current vector potential that is being distributed at a distant point P. by the current equation. So we can calculate in simple word by using the Maxwell equation as del into A is equal to mu h. So when we consider the electric field that is being radiated and the magnetic field that is being generated due to the radiation, it is denoted as h phi and e theta. So h phi is equal to a I m cos pi by 2 cos theta divided by 2 pi r sin theta a by m, and similarly e theta is equal to 120 pi I m cos pi by 2 cos theta divided by 2 pi r sin theta. Actually this is an very big derivation where we need to derive the whole thing, but in this case you have to just know what are the field intensity equations and what is the electric field equation for the radiation that is being generated. So by applying the Poynting theorem again, the maximum value of the Poynting theorem is given as P max is equal to E theta h phi. So by using this particular equation, we can go for calculating the Poynting vector. The radiation resistance of this particular half-wave dipole is given as 73 ohm, and the effective aperture is given as 0.13 lambda square, and the directivity gain that is obtained by using this particular dipole antenna is 1.63. So coming to the next type of antenna, that is loop antenna. So as the name indicates that loop antenna is nothing but, we can say that loop is in the sense coil. So that is a radiating coil for any convenient cross section of one or more turns that carries the RF current. There are different types of loop, that is you can see in the PPT, that is circular loop or rectangular loop, or either it can be square loop. So depending upon our need, we can go for choosing what type of loop antenna that we want to use for the particular application. So depending upon the application, the loop antennas can be varied. So now we will see the radiation field of small loop and its radiation resistance. So initially we are taking a path difference, you can see in the diagram. So we have taken the path difference as d sin theta and as well as the phase difference beta d sin theta, where E phi is equal to 120 pi square L sin theta A divided by R lambda square. So this is actually the electric field and the magnetic field, as we saw in the earlier. E phi and H theta is being denoted, where A is equal to L into D. Okay, so this is how we will be calculating the radiation field of small loop antenna. So now students, this is up to you. These are the possible questions that can be expected from this particular topic. So that is explain various antenna designs, and then radiation mechanism of antennas, and also explain radiation